Hello everyone, today a video on acids and bases and specifically buffer solutions. So buffers are solutions that resist changes of pH when small amounts of either acid or base are added. The pH remains almost constant. And so buffers are designed to keep the concentration of hydrogen ions and hydroxide ions in a solution almost unchanged. And they're based on the type of equilibrium reactions that we've been looking at throughout this whole topic. And these equilibrium reactions will move in the direction to remove either additional acid or additional hydroxide ions that are added. So first of all, looking at acidic buffers. Acidic buffers are made from weak acids. So if we consider the standard dissociation of a weak acid, HA, remember that the equilibrium lies well to the left. Weak acids are only partially dissociated, so we have HA dissociating into H plus and A minus. We know using our assumption of a weak acid that we know that our H plus concentration is equal to our A minus concentration, and that they are both very small because it's a weak acid and therefore mostly undissociated. So if a little base is added, the hydroxide ions will react with the weak acid HA to produce water and A minus, the standard neutralization reaction. This removes any added OH minus, and so the pH tends to remain almost constant. On the other hand, if we add some acid, a little acid, the equilibrium will now shift to the left. The H plus ions will combine with the A minus ions. We use the Chatellier's principle. We've added more acid. The equilibrium wants to oppose that change by reacting more of those H plus ions with the A minus ions. Equilibrium shifts to the left. This produces more undissociated HA. However, the A minus concentration, as we said, is very small because it's a weak acid, and so the supply will soon run out. So the way to get around this is to add in an extra source of A minus. And the way we do this is by adding a soluble salt of HA, which fully ionizes to give us lots of A minus ions. So for example, if the weak acid was ethanoic acid, CH3COOH, the salt could be sodium ethanoate. Now this produces lots more A minus ions, and so the A minus concentration increases such that any added acid, any added H plus, the pH tends to remain almost constant. So the sort of takeaway headlines is that an acidic buffer is made from a weak acid and a salt of the weak acid, which we can make from a weak acid and a strong base. For example, the sodium ethanoate salt could be made by taking ethanoic acid and reacting it with sodium hydroxide. And it will maintain a pH of below 7. It will be acidic. So the weak acid component, HA, removes any added base, HA plus OH minus going to A minus and water, and the salt component removes any added H plus. A minus plus H plus goes to undissociated HA. The other sort of side of the coin of this is a basic buffer. Now we make this from a weak base and the salt of a weak base. And the salt we can make from a weak base and a strong acid. So for example, if we take the weak base, for example ammonia, the weak base will remove any added acid, so NH3 reacting with H plus to produce the ammonium ion. And the salt component, so for example if we're using ammonia, we can take our weak base ammonia, add a strong acid like HCl to make the ammonium chloride salt. This removes any added base, and it's the cation part of this, the NH4 plus, that reacts with any added base to regenerate the weak base and water. So again, the takeaway headline is that a basic buffer is made from a weak base and a salt of the weak base, which is made from the weak base and a strong acid, and it will maintain a pH of above 7. And so if we say that the base is B, the weak base removes any added protons, so B plus H plus to BH plus, and the salt component, which we can say here might be BH plus, removes any OH minus to produce the undissociated weak base B and water. So the equations are quite similar, almost kind of reversed between the basic and acidic buffers. So make sure that you can write out the equations for when acid and base is added to acidic and basic buffers, and also how these buffers are made. The takeaway message is that we always need the weak base or acid and a salt of that weak base or acid. We need both components. Now buffers don't ensure that no change in pH occurs. The addition of some acid or some alkali will still change the pH, but only slightly and by far, far less than adding the same amount to a non-buffered solution. It's also possible to saturate a buffer, so this is where we add so much acid or base that all of the available HA or A- is used up if it's an acidic buffer. So while we think about the fact that we can add lots of it and the pH doesn't change, there will come a point where we simply run out of how much we started with. Now there are lots of examples of buffers, and there are, one of the most important ones and naturally occurring one is blood. So the pH of blood is maintained at approximately 7.4, and a change of as little as half a pH unit could be fatal. And the most important reaction that goes on in the blood is the equilibrium reaction here of protons with these HCO3- ions, these hydrogen carbonate ions. The reaction of that, the equilibrium, produces CO2 and water. And so we can see that if we add any extra H+ ions, this is going to move the equilibrium to the right, which actually, as principle, says that we want to oppose the change, and so the equilibrium shifts to the right by reacting these extra H+ ions with the HCO3- ions. And if we add any extra base in, well, this moves the equilibrium to the left because the H+ ions react to form water, and so we need to then essentially make more of the H+ ions to oppose that change, and so the equilibrium moves left. This is also the same equation that acts to buffer the acidity of soils as well, so the same kind of buffer reaction happens in soils as it does in blood. And there are many other examples of buffers in everyday products such as detergents and hair products like shampoo. And if these substances become too acidic or too basic, then obviously they could damage fabric, they could damage your skin, they could damage your hair, which is all very bad. So now we come to the kind of real meat of this and actually calculating some values for buffers. So if we consider an acidic buffer, since it's a weak acid, we can do what we did in the weak acid video and simply write an acid dissociation constant expression to calculate the pH. So we have our Ka is equal to H plus A minus over HA concentrations. That's our simple equilibrium expression of concentration of products over concentration of reactants. However, we don't just have the weak acid present, we have also the conjugate base, the salt, present. So we can't use the simplification like we did for just calculating the pH of weak acids, that the H plus concentration equals the A minus concentration, because now we have a lot more A minus than we do H plus. So we can't write the top line as H plus squared. So the way to go about calculating the pH in questions like this is to treat this like an equilibria calculation. And so to work out the moles at the start and to work out the moles at equilibrium from the data given in the question. So if we have an example here where we're calculating the pH of a buffer solution formed from 500 centimeters cubed of a 0.4 mole per decimeter cubed sodium hydroxide solution being added to 500 centimeters cubed of a 1 mole per decimeter cubed benzoic acid solution. And we're given the Ka there for benzoic acid. So this is the creation of an acidic buffer. We have our weak acid, benzoic acid, reacting with sodium hydroxide to produce the salt, C6H5COO- Na+, and water. It's a neutralization reaction. But the key thing is it's a buffer. We have our weak acid and we have the salt of the weak acid. So the first thing that I would do is to calculate the moles of each component at the start. So we're given enough data, we're given the concentration and volumes to work out the moles of acid and base. We're going to use our equation N equals CV to work out the moles, remembering to convert our volumes from centimeters cubed into decimeters cubed by dividing by 1,000. So putting those numbers into the N equals CV equation gives you 0.5 moles of acid and 0.2 moles of base. Now the important thing to do here is to look at which one is the smallest number. The base is the smallest number, and so this is the limiting reagent. This is the one that gets used up completely and essentially limits how much product you can form. So we know we have 0.5 moles of acid and 0.2 moles of base present at the start. Therefore, at equilibrium, the limiting reagent will be completely used up. It's the smallest number. So the 0.2 goes down to 0 for the sodium hydroxide. We also need to really importantly look at the mole ratios. Now in this question, all the mole ratios are 1 to 1. So if we've used up 0.2 moles of our sodium hydroxide, we must have created 0.2 moles of the salt and 0.2 moles of water. And then if we've used up 0.2 moles of the base, that is because it's a 1-to-1 ratio with the acid, so we would have used up 0.2 moles of the acid. So 0.5 divided by take away 0.3, sorry, gives you 0.5 minus 0.2 gives you the 0.3 moles of acid that you are left with at equilibrium. So now we go and write out our Ka expression. So we have H plus C6H5COO minus divided by the benzoic acid, the unreacted acid. So the acid number that we put in is going to be the number that is unreacted, because we're concerned about what the moles are at equilibrium when the buffer solution is formed, not at the start. And the top, our H plus concentration, well, that's what we want to work out because we're looking to find the pH. Remember that pH is the negative log of the H plus concentration, so we need to rearrange our expression for H plus. And the C6H5COO minus is the salt moles that we have. So we rearrange our expression for H plus, we times our Ka expression by concentration of unreacted acid, divide by the concentration of the salt, and we get that our H plus concentration is equal to Ka times the concentration of the unreacted acid divided by the concentration of the salt. Now the really key thing here to do is to always remember that these are concentrations, not mole values. We've been dealing with mole values when we've worked out our kind of equilibrium values, and so we have to convert our moles back into concentrations. And so the way we do that, N equals CV, so our concentration is going to be equal to the moles divided by the volume. And the key thing is that we need to convert our volume from centimetres back into decimetres by timesing by 1,000. And so you can see that in our expression we have our Ka multiplied by the unreacted acid concentration, which would be 0.3 moles times 1,000 divided by 1,000. Now the important thing is also to remember what the total volume of the solution is. So we've started off with 500 centimetres cubed of acid, 500 centimetres cubed of base. So when they're added together, the total volume of the solution is 1,000 centimetres cubed. That's another really key mistake that is often made, is that people don't consider the total volume of the solution. What is the total volume? It's when you've added the acid and base together. So when you do that calculation, we find that our H plus concentration comes out to be 9.45 times 10 to the minus 5 moles per decimetre cubed. So we have H plus concentration, so we then just have to work out the pH with the negative log of that. And when you do that, you find that the answer is 4.02. Remember to give pH to 2 decimal places. So we can also calculate how the pH changes when acid is added to this buffer. So suppose I add 10 centimetres cubed of a 1 mole per decimetre cubed solution of HCl to the buffer on the previous slide, which remember had a pH of 4.02. The H plus ions will react with the conjugate base. Remember those equations that we looked at right at the start of this video. The H plus ions react with the conjugate base, the benzoate A minus ions, and they form molecules of undissociated benzoic acid. Now, in the following calculation, I'm going to ignore the volume of the HCl that's been added. Remember, the total volume is 1,000 centimetres cubed from the previous question. By adding in 10 centimetres cubed, it's only a 1% change. It's a reasonable assumption to be able to ignore that. Also remember from the previous slide that at equilibrium, when this buffer is formed, we have 0.3 moles of acid and 0.2 moles of salt. So we calculate the moles of HCl that we've added. So we take the volume times by the concentration, divide by 1,000 to convert our volume from centimetres cubed into decimetres cubed, and we've added 0.01 moles of the acid. So our acid, HCl, remember HCl is a strong acid, it fully dissociates. So the HCl moles will add to our acid concentration. They will make the H plus concentration bigger, but they will react with the salt concentration. They will make that lower. So now the moles of acid is the 0.3 we had originally, plus the 0.01 to give 0.31 moles. And the salt will go down. So we have 0.2, we take away the 0.01, and we end up with 0.19 moles. Now all we do is repeat the calculation we did before with these new mole values. So we rearrange our Ka expression for H plus. That gives us our H plus concentration as Ka times the acid concentration divided by the salt concentration. Again, remember that we have to convert the mole values we've been dealing with back into concentration. So we need to times by 1,000 and divide by 1,000. The times by 1,000 is to convert to get these concentrations in moles per decimeter cubed. And the dividing by 1,000 is the volume of the solution, which is 1,000 centimeters cubed. So again, it will cancel out in this case. Once we do that calculation, we end up with 1.028 times 10 to the minus 4 mole per decimeter cubed concentration. And so to find the pH, simply the minus log of that, which comes out as 3.99. So you can see on adding 10 centimeters cubed of this strong acid, we've only changed the pH by 0.03. So a very, very small amount. Now I repeated the calculation and I accounted for the extra 10 centimeters cubed. So the total volume that I used when I convert my moles back into concentrations was now 1,010 centimeters cubed. And to the 2 decimal places that we have to give pH values to, remember, the answer is 3.99. So it was a reasonable assumption to just use the old total volume. So one way to achieve a mixture of the weak acid and the salt is to neutralize some of the weak acid with a base. This is what we've been doing in these past questions. We've been taking our weak acid and a base, reacting them together and making the salt, and we get both components. Now, if we neutralize half of the acid, we'll end up with a buffer where the pH is equal to the pKa of the acid. Now, if you're unsure about this, go back to the previous video in this series where we looked at the fact that at half neutralization, the pH is equal to the pKa. And so at this point, it has an equal supply of undissociated acid and the A-, the salt anions. Now this is a very useful buffer because it's efficient at resisting change in pH whether acid or base is added. And it's also useful to know how to make a buffer solution to a specific pH. And this can be achieved by using something called the Henderson-Hasselbalch equation. So let's say we want to make a buffer that has a pH of 4.5. We write our Ka expression, H plus A minus over HA, rearrange for H plus because again we're interested in pH. So we have Ka times HA over A minus when we've rearranged that equation. And now what we're going to do is we're going to do the negative log of both sides, essentially P. Remember that pH was the negative log of the H plus concentration, pKa was the negative log of Ka. So if we take the negative log of both sides, we end up with the negative log of H plus, meaning pH. And then using our law of logarithms, we can separate out the Ka and the concentration parts. So we now have pKa. And then we have this ratio of the concentration of HA and the, over A minus. And so our equation becomes pH is equal to pKa minus log of the ratio of HA over A minus concentrations. So what this tells us is that if we pick an acid with a pKa roughly around the pH, we can make a buffer of a specified pH. So we make sure we pick one that has this pKa around the pH. In this case, benzoic acid is pretty good. It has a pKa of 4.2, pretty close to the 4.5 that we want. We can stick these numbers into our equation. So 4.5 is equal to 4.2 minus the log of that ratio of concentrations. We can rearrange such that the log of the concentration ratio is 4.2 minus 4.5, which is negative 0.3. And then we take the anti-logs like we did when we wanted to find out some of the values with the H plus concentrations from pH. We take the negative log of both sides. So we do 10 to the power of log of the ratio. The 10 and the log cancel out. And we're just left with the ratio of HA and over A minus concentrations. And we do 10 to the power of negative 0.3. And if you do that in a calculator, you get the answer of 0.5. So what that tells you is the ratio of HA over A minus concentrations must equal 0.5, i.e. you need to have double the concentration of A minus compared to the concentration of your acid that you put in. Now this equation is very useful for being able to calculate if you want to make a buffer of a specific pH. You can also use this equation to answer the questions that we've had on the previous slide. If you're asked to work out the pKa of a specific buffer solution, well, as long as you work out what the concentration of your acid at equilibrium is, what the concentration of your salt at equilibrium is, and you're given the Ka so you can work out the pKa, you can work out the pH using this equation as well. So it's completely up to you. I always prefer to use the actual kind of equilibrium calculation and work it out a bit more. But if this is a better way of doing it for you, then you can also use this equation. So it's time to have a go at some questions. If you want to have a go, pause the video, and then the answers will be on the next slide. So the first one is to calculate the pH of a buffer solution containing ethanoic acid and potassium hydroxide, and then to calculate the pH when we add some acid to the buffer solution that is formed. So the first part of this question then is to calculate the pH of this buffer solution. So again, I'm going to go through the way of doing it using the kind of equilibria calculation style. If you've done it using the Henderson-Hasselbalch equation, that's equally fine. The way I'm going to do it is start by writing out the equation. So ethanoic acid plus sodium hydroxide. The equilibrium reaction produces sodium ethanoate, the salt, and water. We have enough data to work out the moles of acid and base at the start of the reaction using the N equals C times V equation. Again, remember that we have to convert the volumes from centimetres cubed into decimeters cubed for that equation to work. And so putting the numbers in gives you 0.05 moles of acid and 0.01 moles of base. Again, the 0.01 mole is the limiting reagent, it's the smallest number, that's going to limit how much product we can form. And so at equilibrium, we're going to use up all of our base, so 0 moles at equilibrium. It's a 1-to-1 ratio in the equation again, so if we've used up 0.1 moles of base, we must have also used up 0.1 moles of acid, so the equilibrium amount of moles is 0.04. And then if we've used up 0.01 moles of our base, we must have created 0.01 moles of our salt and 0.01 moles of water, again because they're all in a 1-to-1 ratio. Then we write out our Ka expression, H plus CH3COO minus divided by CH3COOH. So that's the the H plus concentration multiplied by the salt concentration divided by the unreacted acid concentration. We rearrange that equation for H plus because we're interested in pH, and so when we then put the numbers into that rearranged equation, again remembering to convert the fact that we were dealing with mole values back into concentration values, and remembering that the total volume of the solution is now the 100 centimetres cubed of the acid plus the 50 centimetres cubed of base, so 150 centimetres cubed. The H plus concentration comes out to be 7.2 times 10 to the minus 5 moles per decimetre cubed. So the pH is a very simple calculation, just the negative log of that, and the pH comes out to be 4.14. Again, remember pH to 2 decimal places. The second part of the question looked at when we add some acid to this buffer solution. So remember that we have our original acid being 0.04 moles at equilibrium, and our original salt at equilibrium being 0.01 moles. We work out the moles of the acid that we have added. Now again, this is where we have to be careful. On the previous videos we looked at a sulfuric acid question. Sulfuric acid is diprotic, it releases 2 moles of H plus per mole of sulfuric acid. So we can work out our moles doing the concentration times the volume, which gives our moles of sulfuric acid as 0.001. But sulfuric acid is diprotic. 1 mole of sulfuric acid, 2 moles of H plus. So that means the number of H plus moles that we've added is actually 0.002. Now again, this is an acidic buffer, so if we add some acid into our buffer, the added H plus ions are going to increase the acid moles, but decrease the salt moles, as they will react with the salt, the A minus, to produce undissociated HA. So we add the moles to the acid to give a new acid moles of 0.042, and we take away the moles from the salt to give a new salt moles of 0.0080. Again, we now repeat the calculation. We write our Ka expression, we rearrange for H plus plug in the numbers, again remembering to convert the moles back into concentration. Now in this case I have used the new volume because it's a slightly bigger change in the volume. Remember last time it was 10 centimeters being added into 1,000 centimeters cubed. Here we have 10 centimeters cubed being added into 150 centimeters cubed, so a slightly bigger change. So I've included it this time. When you calculate that equation, you end up with 9.45 times 10 to the minus 5 moles per decimeter cubed for your H plus concentration, and so then the pH is the negative log of this, and it comes out to be 4.02. So again, not so much of a big change because it's a buffer solution. So thank you for watching this video. You can find many more like this on my YouTube channel. I hope you found it helpful. If you have, it would be great if you could leave a review on one of my tuition websites. I offer online tuition for chemistry, so please check out my tuition pages if you're interested in that. And if you need any more help with your chemistry, feel free to drop me an email. I'm always happy to help.